with Nick Hutchins. And first of all, I'd like to thank the researchers, the PhD students and postdocs who performed the research. Especially like to acknowledge Sebastian, who made a major contribution here. I also like to especially acknowledge Ricardo for his major contribution also to our work on Riblets. So Ricardo, thanks for teaching us about Riblets and generously providing us with your good ideas. This project is supported by the Australian government through the Australian Research Council and also supported by the Air Force Office of Scientific Research. And we've been using supercomputing time from the Australian Facilities Policy and NCI. Okay, so I'd like to talk about Riblets and rough wall heat transfer. And I'd like to talk about how in particular we got from where we stood to beyond current boundaries using minimal channels. And this is possible because minimal channels provide drag and heat transfer and flow data at the same time in a cost-effective way. Just quickly for now, like minimal channels are tiny boxes in which we perform simulations. They're much smaller compared to the normal full-size boxes. So let's start with some background. So Riblets are now mature technology that you can find them being applied. However, there's still questions about how they work. And so as we'll see later on, but Riblets are not shark skin. Okay, so they're not shark skin denticles. In fact, they're just grooves. Okay, they align with the flow in the x direction. And Z is the wall normal direction. And if you resist this notation, I shall read to you what Townsend has to say. And I quote, "I offer them my sympathy, but not my repentance." So these Riblets are tiny, right? So compared to the near wall structures, which are 100 wall units, these Riblets are much smaller. So they're about 5 times smaller. And this translates in practice to about 100 microns. So you can't see them with your eyes. All you see is a dull surface. Okay, so now to design for Riblets, we need data on a plot that looks like this. Okay, so this shows percentage drag reduction or fractional change in skin friction coefficient versus size. So here I'm using S, the spacing, and plus means non-dimensionalization with viscous units and the friction velocity. Okay, so I'm showing here now data compiled by Ricardo for various cross sections. Okay, and straight away we see 2 trends. The first is that the optimal spacing, which are the lowest points here, depends on the cross-sectional shape. The second one is all these shapes follow a similar behavior. So let's just focus on one for now. For small Riblets, we know that drag reduction increases with increasing size. And the behavior here follows Lucchini's theory, who's sitting here today. And the theory says that the slope of this line follows something called the protrusion height difference. And this protrusion height difference can be tabulated. They're known from, if you know the Riblet geometry, you know this number. Okay, they're computed from simple Stokes calculations. Now, if you increase the sizes, at some point it hits the optimum, okay, and drag reduction breaks down. Now, there are many explanations of it for this behavior. I'm just listing the ones here that provide quantitative prediction. And in particular, over the next moments, I'd like to focus on just one. And this is the one by Ricardo and Javier Jimenez. So it says that I break down Kelvin-Helmholtz instability forms. Okay? Oh, question? So the spacing is about 20, the height's about 10 wall units. Yeah. Yeah, so so these Kelvin-Helmholtz structures are familiar, right? We see them in clouds, for example. And here's a top-down view from Ricardo's DNS showing the wall normal fluctuations, okay? And you can see for reference, Ricardo's put in the location of the blades here, okay? And straight away you see that these coherence in the spanwise direction. And the other thing you notice is their spacing is about 150 wall units. Okay, There's a difference between the rollers that appear over riblets compared to the ones that are shown in clouds before, and that's because these rollers appear next to a wall. And we know from early studies that rollers cannot form over impermeable walls. And so in fact, Ricardo showed that for riblets, riblet surfaces are actually effectively porous. And he showed that the permeability or the porosity or the wall admittance is proportional to this number Lg cubed, where Lg is defined in this following way. So if you take the cross-sectional area of the riblets and you take the square root, that's Lg. Okay, and so this idea suggests that as we increase the riblet size, once Lg gets to a critical number, these Kelvin-Helmholtz rollers will be triggered. Okay, so we quickly go back to the data that Ricardo compiled and plot it against Lg instead of S. And you see, so this is S, and this is Lg plus, and straight away you see a much better collapse. And the optimum now is at around 10 wall units. Okay, and so when we became interested in riblets about 5 years ago, our idea was to try and perturb these Kelvin-Helmholtz rollers, try to destroy them, mitigate them, do something to them to obtain further drag reduction benefit. Yeah, question? It doesn't matter for now. I'll put proper numbers later on. This is just a generic curve right now. Yeah, this number will depend on Reynolds number. So I'll talk about it. Yeah. So, so to do this, we need to track two things at the same time. One is the drag reduction and the appearance of these rollers, and we need to do that in an cost-effective way. So if you look at the data that we had that Ricardo compiled, you see that the experiments allow us to test many shapes. However, we can't see the rollers in this experiment. And then from the DNS, you get the drag, and you can see the rollers, but you can only do them for one geometry because they're really expensive. But if you look at the DNS performed by Ricardo at higher Reynolds numbers, you see that these rollers scale with viscous units. And so that's when, at the time, we thought it would be a good idea to perform simulations in these minimal channels here, okay? And because they're minimal, they allow us, they're more cost effective, they allow us to test more riblets, riblet shapes, okay? Now, before you're thinking that we're taking shortcuts, actually we're doing the opposite. So maybe it's not so familiar to some of us that simulating flow over riblets is actually much more expensive than simulating flow over a smooth wall. So here I'm showing actually the coarsest grid for the cases that we have. And for the drag reducing case, the span-wise resolution is actually 10 times finer than what would normally be used in a smooth wall DNS. So these are not cheap simulations if we want to resolve the riblets. Okay, so talk quickly a little bit about how the minimal channel works. Okay, so here's just a normal full-size channel with a smooth wall. Here's the mean velocity profile. Okay, and now I'm showing a minimal profile. Okay, and straight away we see that near the wall, these profiles agree up to a point. And thanks to work by Javier and Yongyun, the trick with minimal channel is this location can be controlled by the span. Okay, in fact, it's 40% of the span. So here, 250 times 40%, that's 100. So this means if we perform minimal channel simulations over riblets with the same span, we'll get a behavior that looks like this. That's accurate. So the flow is accurate up to z plus equal to 100. Okay, importantly, that's enough for us to measure delta U plus, the shift in the velocity accurately. Okay, and this delta U plus, Marcus's question, this is proportional to the drag reduction percentage. Okay, but the benefit of this quantity delta U plus is we don't have to track its Reynolds number dependence. So for example, it's well known that riblets drag reduction in a lab is say you get 10%, that's actually 5% in application. But delta U plus equals 1 is always equals to 1. So I'm going to show only delta U plus from now on and putting on some contemporary data, some obtained from Bettina von Napfol's group at Karlsruhe, and then these ones are Ricardo's DNS as well. Now I'm going to put all our data on. Maybe a little bit overwhelming, but I'll visit each of those points later on. But for now, I just want us to notice there are many shapes and sizes. So we have 3 triangular riblets with different tip angles. We have the trapezoidal riblets, which are known to have good performance. So they're the lowest point here. And also blade riblets, which are like Ricardo's. And then also for kicks, we put in some asymmetric riblets. Okay, so now with all these cases, it's time to hunt for the Kelvin-Helmholtz rollers, right? So we can stare at colorful fluid dynamics for the next couple of minutes, or we can go straight to the spectrum. So here I'm showing the 2D spectrum as a function of span-wise and stream-wise wavelengths, okay? And for Kelvin-Helmholtz rollers, we want to pay attention to this box here, which represents large lambda wide, so they're wide structures, and the spacing is centered around 150 wall units. Okay, so now for reference, I'm putting on smooth wall co-spectrum actually, so that integrates to the Reynolds shear stress. And the plane where we're taking this co-spectrum is 3 units above the smooth wall. Okay, and you see there are no Kelvin-Helmholtz activity, there's nothing in there. But if I plot the same thing over blade riblets, straight away you see Kelvin-Helmholtz activity. And for your reference, I'm marking here the spacing of the riblets, okay? So what happens with size? Oh, before that, you can compare also with Ricardo's full channel DNS, okay? So back one, this is minimal, this is full channel DNS. So I would say they're pretty consistent. Okay, so let's look at the effect of increasing size now. So this is quite a busy plot. So over the top, I have all the riblet cases for the blade geometry shown here. And I've marked in those boxes again, very important, watch the boxes. And for the smooth wall on the left, okay? And all the data points are here, but the ones that are highlighted in color correspond to the riblets that are shown here, corresponding to the co-spectra up there, okay? And this is the drag penalty versus riblet size as I've shown before. And so let's check the idea. So at onset, you do see the emergence of these Kelvin-Helmholtz rollers, and then as the size increases, they become active, okay? Now, those are for the blades. See what happens when I go to the asymmetric riblets. Look at the boxes. They're all gone. Okay, so even though the drag penalty is increasing, there are no Kelvin-Helmholtz activity in there. So before you think that it's something weird going on with the asymmetry, let's look at the trapezoidal riblets. Also nothing in there. Okay, even though the drag penalty increases. Okay, now going back now to the sharp triangular riblets, you do see actually very strong Kelvin-Helmholtz activity. Okay, so then now what happens if I blunt the tips of the riblets? So this is blunter, they disappear. Okay, I go blunter again, they're gone. Okay, so I could show you convergence with proper numbers, or I can show you convergence in the picture norm. Okay, so here, all this is saying is that whether you have Kelvin-Helmholtz rollers or you don't have Kelvin-Helmholtz rollers, they don't depend on the box sizes. Okay, so for more details, we do a very exhaustive comparisons convergence study in this paper. Okay, so one thing we need to get to is the drag penalty from the Kelvin-Helmholtz rollers. What I've shown here are just Reynolds shear stress co-spectrum taken at a wall location. So that's not equal to drag penalty. To get that, we need an equation that looks like this, okay? This is similar, for example, to the FIK identity for the skin friction coefficient, but this one's written in terms of delta U plus. Okay, it has 2 components, so you can interpret it this way. So for the total drag penalty, that's equals to the mean slip component taken at the crest, and then this component, which is the difference of the Reynolds stresses integrated in a wall normal direction. Okay, now this quantity, the difference of the Reynolds stresses is 0 far away from the riblets because of outer layer similarity. Okay, so we can evaluate this quantity pretty well. So here's how, and we need to tease out the Kelvin-Helmholtz aspect part of this contribution. So we can look at it in spectral space. This is how it looks like. So this is again the wall normal integrated difference of the Reynolds stress co-spectrum. Okay, and so if we want the Kelvin-Helmholtz contribution, we just look in the box up there, which corresponds to structures like this. So let's look at all the drag penalty contributions now. So these are for those sharp triangular riblets, okay, which show, and they show right after the optimum an increase in this drag penalty contribution. These are the blade riblets from minimal channels, and these are Ricardo's full channel simulations at different Reynolds numbers, and you can see they're fairly independent of Reynolds numbers and box size. And now I'm showing all the other riblets, and you can see that they don't contribute too much. Now, if I rescale the y-axis so that it matches the total drag penalty, you can see that they make some contribution, but they don't explain everything. Now, I don't have time to talk about why we get rollers or why we don't get rollers, but some clues can be found in this paper. I'd like to talk a little bit about secondary flow, which is an older idea, which was proposed in the past as and considered to be associated with drag increase of riblets. Okay, so secondary flows are just time average flow structures. You will never find a structure like this when you look at the flow instantaneously. These are time average, but because they fluctuate in space, they create some kind of stress. Okay, and that stress is called the dispersive stress, and associated with this dispersive stress is a dispersive drag penalty. Okay, so if you look back at this map of all the contributions, the dispersive drag penalty lives here because they're infinitely long and they have a period that's equal to the riblets because they are caused by the geometry of the riblets. So you can consider this effect to be a shape-induced stress. Okay, so we can compute these secondary flows, and we're showing the stream function here with increasing size, and the ticks are drag reduction, crosses are drag increase. So, and you can see that they start to appear with drag increase. And indeed, if you look at the drag penalty from these guys, you see that they increase too. And then for comparable sizes, you can also look at the effect of blunting the effect of the tips. And you see they also grow. And the message from the dispersive drag penalty is also the same. One thing to note here is they have an inverse relationship with the Kelvin-Helmholtz rollers, right? For the Kelvin-Helmholtz rollers, they were the strongest here, whereas for these secondary flows, they're the strongest here, okay? And so we can compute these quantities for all our cases and plot all the contributions here, and then rescale it and compare it with the total drag and as well as the Kelvin-Helmholtz contribution. So we can see that they make some contribution also to the total drag penalty. Now there's a caveat here. Because these come from secondary flows, which are time average motions, it's hard to say something about cause and effect, okay? At best, we can say these are probably signatures of some mechanism. But from this exercise, what we can say is that whatever the mechanism is, it will have a dispersive drag penalty signature. And that signature will depend on size, and that signature will depend on geometry, and that signature will have a spanwise velocity component, okay? And so this is still work in progress. We're trying to still figure out what the exact mechanism is, but I can tell you what I'm reading. So some of these are consistent with the character of what I described before. And in fact, Mihailo is sitting in this room today. And this thesis was supervised by Denise, who's also sitting in this room today. So I invite you to talk to them. How much time do I have? We have about 4 minutes before we get to practice. Okay, so I'm going to skip. Sorry, Jeremy, if you're watching this. I'm going to skip Jeremy's results for tiny riblets. No, I'm sorry. Well, 4 minutes before I give you the 5-minute warning. Oh, yeah. Oh, I've got plenty of time. Okay. Okay, I take that back. So I do actually have time. Okay, I'll go slower now. So I actually wanted to talk about oversized riblets as well, but I thought I didn't have time. But I want to talk about tiny riblets. This is interesting. So I said that the drag penalty was proportional to the protrusion height difference before, okay? But I didn't talk about the constant of proportionality, okay? And that constant of proportionality is actually called mu naught in the literature. However, in the literature, when you look at this number, there are different numbers that are quoted for it, okay? And this is kind of puzzling, okay? And so the way to address this is to have, high quality, accurate, direct drag measurements data in this regime. But before I plot that, what I'm gonna do is normalize this formula so that I'm compensating it so that when I plot this compensated drag penalty versus LG, the size, I'll get a slope that is mu naught. Okay, so now I'm showing Jeremy's data. in this more Riblets regime. And straight away you see, I don't want you to focus on any particular single curve, but just to look at the spread. And you can see maybe a reason for why the different values have been quoted in the past. And because this is, you know, they go through all the scatter, okay? But now with the DNS data, we can actually go into the flow and actually test the underlying physical ideas on what's actually going on and what's different about the theory versus what we see. Okay, so with the last maybe 5 minutes, 5-6 minutes that I have, I'd like to talk about heat transfer over rough walls. So rough wall heat transfer has many applications. Here I'm showing one frightening application, and that's ice formation over an aircraft wing. Okay, they're a safety hazard because they change the shape of an airfoil and modify its aerodynamic performance. Okay, and the key to predicting the formation of ice is this from this review paper is this quantity, the convective heat transfer coefficient. Okay, and that means we need to solve this problem here. Okay, so given a mean convection or mean flow and mean temperature difference relative to the wall for a roughness size that's proportional to Ks. Okay, what is the heat transfer QW? That's what we like to find out. Okay, so this problem has been solved, has been measured for the smooth wall, and so all we need is the difference between a smooth wall and this rough wall value. Okay, for both for the velocity and for the temperature. Okay, so as I've introduced before, this roughness function for Riblets, for roughness, it actually goes the other way. So delta U plus is positive. Okay, as Angela's talked about before as well. And so we can do exactly the same thing with temperature. Okay. And also the minimal channel ideas, this control location can also be applied without further modifications. Okay, so let's look at delta U plus and delta theta plus versus the size now. Okay, so just a review. So delta U plus, if we plot it versus size, and if we increase the size, it is widely known for conventional roughnesses, for all these different kinds of roughnesses, that we will obtain this behavior where all the symbols will follow this line with log slope 1 and kappa in the fully rough regime. However, if I show you delta theta plus for the temperature, it's all over the place. Okay, and in here you would see popular CFD software. You would see famous textbook models. You would see theoretically argued models. You would see empirical models, and this is only for one Prandtl number. Okay, so this curve will change depending on the working fluid. For example, water or air, this curve will change. Okay, so this is a problem. To solve this problem, to resolve this scatter, we need high quality data. And in fact, all those correlations are calibrated against this data, which you can think of as the Nicorazzi plot for heat transfer, if you like. This data was taken at Caltech in the 1960s, and the roughness is close packed granular roughness for different working fluids. So the ones down here closer to air and the ones up there closer to water. Okay, and here actually they're plotting a function called G, which is related to delta theta plus that I showed before. Okay, so even though all the previous correlations were tuned with this data, they show different behavior. And so the only way to resolve what is actually physically going on is to have access also to the flow. And this has been extremely difficult up till now. And you know what I'm going to do. I'm going to say use the minimal channel. And so without further ado, I'm going to show you some colorful pictures that Kevin Chung prepared. This is in the fully rough regime. The top row is the velocity going from left to right, and the bottom row is the temperature for increasing Prandtl number. So you can see with increasing Prandtl number, the conductive sublayer becomes very, very thin. So for the same reasons again as Riblets, these are not cheap simulations. There's highly expensive simulations to resolve the conductive sublayer. And this is not the minimal domain, by the way. The minimal domain is, you know, it goes further up. Okay, so this is just showing one period. Otherwise, you won't be able to see the conductive sublayer. Okay, so now that we know we have the flow field, let's put our data on here. So we've got sinusoidal roughness, put on sand-grain close-packed granular roughness, and we see pretty consistent behavior. Okay, so for example, for the large roughness regime, you see the asymptote at least behave in the right way, and in the transitional regime, you see these curves the curves are pulling up in the same way as the other data, and you could also see the Prandtl number behavior. So the blue one, Prandtl number is 1, and then existing data here will be Prandtl number 1.2, and then after that, Prandtl number 2. Okay, so it is encouraging, but we need to do more, I guess. But now we can address difficult questions that were posed for a long time. So everybody knows that Reynolds analogy doesn't hold for rough walls, but what does it go to? I think that's a question that we need to start addressing. Our problem is we're running out of PhD students because our borders have been closed for a while. So we're recruiting PhD students if you're watching, and we're recruiting postdocs as well. If you're watching, you like this stuff, you want to solve some big problems that I like, please get in contact. And with that, I'm happy to take questions. Thanks.
Hey, thank you, Daniel. Questions? Go.
Yeah, thanks, Daniel, for a super clear talk. That was terrific for a non-specialist. Can you go back to one of your first graphics where you have the delta U plus going down?
Mm-hmm. I need to make the...
Now, does it make sense to take the asymptotic limit of the spacing going as large as possible? No, not that one. You just, the one when you're going down and...
Oh, you mean...
Marcus asked about the scale.
These ones?
No, the very first one where you had the reference to Paolo Lucchini.
Oh, okay. Yep. And the question was?
Yeah, so I'm looking at that diagram thinking, does it make sense to... get to it.
Yeah, this one.
Yeah, so does it make sense to look at the limit as S plus goes to infinity? And then those black dots should come down to level? Should they come down to level? Indicating there's a maximum?
Oh, so S plus going to infinity.
Yeah, does that make sense?
So you mean going to the right?
Yeah.
Oh.
There should be a maximum, shouldn't it? Because it should come down and level off again.
Why do you say that?
Yeah, no, I'm looking at the dots. I'm looking at the dots. Oh, that's all right. I'm going high.
Oh.
Is it not? Oh, I see. So that limit doesn't make sense.
Yeah. Well, it'll come into this factor if you want to calculate it. But at some point, so this relies on the flow above seeing an homogenized effect. So once it gets too wide and the turbulent structure sees it, that also goes away. So.
Hi, Daniel. Thank you for a really interesting talk. I have two questions. The first one is there's a eigenmode relative to the mean that looks an awful lot like that KH. I mean, it looks like the TS mode. So have you gone in and looked at that and seen how that moves, or the amplification around there?
We are thinking about it.
Yeah.
We're thinking about it. Yeah. Yeah. Ricardo might have something to say. There's neutral mode that's large that sits.
You can look at the amplification, yeah, but you can actually track the eigenvalue that crosses over to unstable relative to the turbulent mean. Yeah, we see that in opposition control, which is kind of interesting too.
Okay.
Yeah.
Okay.
That's right. Yeah. That's right. Yeah, but you can sort of watch it move. Is what I'm saying, and I wonder whether you can track that through the flows there. Right. And then the other part of the question is, have you looked at the pressure fluctuations at all? Because it seems like you have access to those in the way you don't in
we
the
have.
experiments.
Yeah. There's a lot more that I haven't shown. I could. Yeah.
Well, I'd like to talk
There's
to
a lot
there.
more. Yeah.
Okay. Thank you.
We have done that.
This is really cool. So I've done a lot of work on superhydrophobic surfaces and liquid infused surfaces. And one thing that people typically say when they start talking about superhydrophobic surfaces, this is not Riblet drag reduction. That's like the one thing. That please don't confuse us with Riblets. But when I see this, there's a lot of similarities, especially sort of the tiny side of things. It looks exactly like the superhydrophobic. And I'm wondering if it's actually this exact same mechanism as you go to 0 on this plot. That is essentially it's the same mechanism, but like the superhydrophobic surfaces allows you to go to larger LG plus without getting sort of these other secondary motions and things to affect it negatively.
I think it's possible. I'm not sure if anyone's ever computed delta H for superhydrophobic surfaces. It will be quite straightforward to. Oh,
yeah.
I don't know. Okay, there you go.
I think it is. So, but for some reason, these two fields, they really don't like each other, and they want to make a big point that they are very different. But when I saw this, like, this is the same thing.
Yeah.
Oh, okay. So we're going to take a couple more questions on this because there's a lot of interest out there. Just remember, if you're shouting out from the audience, the remote audience can't hear you at all.
Well, thank you, Daniel. I mean, good talk. I mean, can you say something else about the mechanism of these dispersive stresses?
Yeah, I don't know, which is why I had that caveat. I said I was going to start looking at the.
You know something. Come on, you're not telling us. you look there. You know something.
I don't know. I'm sending you look these kinds of papers here. That's why I said I've been sitting with Denise trying to see if she could tell me some of the secrets there. But I don't know. It's going to be I think it will have some kind of span-wise flow. I think, and that's distinct from no matter what you do to Kelvin-Helmholtz type type structures. You will not get the span-wise motion. So I think this span-wise motion will be essential. And so all these here have span-wise motions in the modeling. And they all seem to be able to get these curves. But I guess, one thing I'd like to do is actually go to the DNS, mini-channel DNS data and compare the physics that's sitting, the physics engine that's sitting behind all these models and see whether that's indeed, indeed the case.
I mean, they look very narrow, no? Is el plus equal 10?
Yeah.
Okay. Thank you.
Yeah.
We had one more over here. Yeah, okay. Was it back there? You have one? Sure. Yeah. Okay.
So this is just a very naive question, but when you showed the top view of the kind of the large scale results, it looked like there's some fairly distinct patchiness.
Yes.
In the flow. I just wonder if you could comment on that. So there's kind of a large scale intermittency.
Yes. That's probably a question for Ricardo. We don't have the big boxes. We have the tiny boxes. So what we're doing is time averaging to get the full effect. But we've checked statistically, it doesn't change the statistics, even the spectral statistics that we're looking at. The paper suggested before it looks at all these things very rigorously. Box size, especially, that was one thing that was concerning a lot of people.
Okay, let's thank Daniel again while we get ready for the next speaker.